In this session, we're going to study inverse functions. And three ways that we can consider how an inverse function behaves is, one, the inverse of a function switches inputs and outputs. Two, the inverse of a function undoes what the function does. And three, the graphs of a function and its inverse are reflections about the line y equals x. Suppose we consider a function f that's defined to be just a set of ordered pairs. Let's say 2, 3, 4, 5, 6, 3, and 7, 8. You can see I was really creative with this one. If we switch inputs and outputs, then we will get a set of ordered pairs that looks like 3, 2, 5, 4, 3, 6, 8, 7. Notice in this case that when we switched everything around, we have an x-coordinate that is repeated, namely 3. And it is said then in this case that f does not have an inverse function. Reason for that is that when we switched the inputs and outputs, we ended up with something that wasn't a function. If we do what we just did, and we end up with a function, then f is called a one-to-one function. So this could be characterized by saying a one-to-one function has an inverse that is also a function. One-to-one functions are explored in more depth in a different video, but for now we can suffice it to say what we have just said. Let's consider another function. Let's consider g of x is equal to x plus 3. And if I scroll up, I want to look at this through the lens of the inverse of a function undoes what the function does. Since g of x is x plus 3, it could be said that g adds 3 to any input. And so to undo adding 3, what we would need is a function that then subtracts 3. In that sense, we have this new thing that undoes what g does. In terms of notation, we would denote this g, and it looks like an exponent of -1 of x. It's not an exponent. This is inverse function notation, and this is read g inverse of x, and is appropriately denoted and named because it undoes what g does. And if we consider a table of ordered pairs for the function g, if we input values like 1, 2, and 3, since g adds 3, we will get 4, 5, and 6. If we then do the same thing for g inverse, let's say I put in 4, 5, and 6, g subtracts 3, and so I'll get the numbers 1, 2, and 3 as outputs. And in this sense, we have the situation that the inverse switches inputs and outputs. So we've explored a little bit of the first two descriptors. The third one will come down the road. I want to make another note about the notation. Let's recall that in terms of exponents, x to the -1 is equal to 1 over x and indicates a reciprocal. However, f, what looks like to the -1 of x, is actually f inverse of x. So this is the inverse of f. It is not a reciprocal. Okay, that is to say that f inverse of x does not equal 1 over f of x. And if it sounds like I'm getting a little emotional, it's just because this is a very common mistake that I see. We're going to watch this whole video that indicates how we're going to find and consider the inverse of a function. If it were as simple as a reciprocal, we wouldn't need this video for it. Okay, so keep that in mind. Now, in terms of switching x's and y's, since the inverse of a function effectively switches x and y, it also switches a domain, and a range. So if we consider just a diagram here where we have the domain of some function f on the left, so f maps from the set on the left to the set on the right, then the set on the right would be the range of f. The inverse switches x's and y's. It undoes what the function does. It's kind of like saying, where are you from? For any output, we can figure out what the input is. That being the case, the inverse takes items from the right set and puts them into the left set. And so the range of f, which is on the right, turns into the domain of f inverse. And the set on the left turns into the range of f inverse. So not only are individual ordered pairs x and y switched, but the entire set of x's and the entire set of y's is switched. Let's say in the domain of f we have a value a. Then in the range of f, that would take us to f of a. I could then ask for, using composition of functions, f inverse of f of a. So f inverse, taking us in the opposite direction that f did, would take f of a back to a. A little more concrete. In the last example, we saw a function that mapped 1 to 4 because it added 3. Right? I know it was called g, but just bear with me here. So in this language here, we would say that f of 1 is equal to 4. Then as far as the inverse is concerned, f inverse of 4 is equal to 1, undoing what the function does, switching x's and y's. Now if I compose f inverse with f of 1, then that's saying to take 1 to 4 using f, that's the inside, the argument, and then f inverse is asking us to apply the reverse. Where did 4 come from? It came from 1. Here's the kicker. Composing a function with its inverse spits back the original input. And so generically speaking, we could say that f composed with f inverse of some value x is the same thing as f inverse composed with f. If you're going to go back and forth, it doesn't matter which way you start, of x, then the answer is going to be x itself. Then we're going to see that as a way to verify that we have found an inverse in a few minutes. Right now what we're going to say is, if f is 1 to 1, then we can find f inverse if we switch x and y and solve for y. In some books, this is imaginatively called the switch and solve technique. So let's consider a function f of x is equal to the square root of x minus 3 plus 4. The domain of f is going to be numbers such that the radicand doesn't go negative, and so consists of 3 to infinity with a square bracket at 3. The range of f, since the radical has a smallest value of 0, the range of f is going to be 4 to infinity. We could graph this, and actually we will in a few minutes. We're going to use this domain and range to help us graph. Actually, we're going to use transformations, but it's all the same stuff, really. We're going to switch x and y and then solve for y, the switch and solve technique. First, we got to remember that f of x was another name for y. So when I switch x and y, what I'm doing is I'm switching x and f of x, if you like. So I'm going to rewrite this as x is equal to the square root of y minus 3 plus 4. Right? So we have now switched x and y. Now I'm going to solve for y. So we have x minus 4 is equal to the square root of y minus 3. Right? I subtracted 4 from both sides. And then I'm going to square both sides. So we have x minus 4, the quantity squared, is equal to y minus 3. And then finally, to solve for y, I'll add 3 to both sides. I'm writing down a step that I would normally skip, but I want to make sure that everyone's on board here. Y is equal to x minus 4, the quantity squared, plus 3 for adding 3 to both sides. I reversed the whole equation. And then finally, we're looking for f inverse, and so it's appropriate to give it an inverse function notation, right? We could be dealing with g or h, and so we want to label it appropriately. F inverse of x is equal to x minus 4, the quantity squared, plus 3. So this is the inverse of f, and we can consider the domain and range of f inverse. We're going to do so from the perspective of, remember where it came from. So we have a domain of f inverse and a range of f inverse, but each of these is tied to an original function f. As it turns out, the domain of f is the range of f inverse, and the range of f is the domain of f inverse. And so if we have already computed or figured out the domain and range, we don't have to think about it anymore. We can rewrite what was already there. So the domain of f inverse is going to be 4 to infinity, and the range of f inverse is going to be 3 to infinity, again with square brackets at the endpoints, because we do actually have those values as part of our intervals. Now, as far as set notation, scroll up just a little bit, we could write the domain of f as the set of x such that x is greater than or equal to 3. But when we switch that to saying it's the range of f inverse, we have to remember that the range refers to y values. So while it's the same interval, it's got a different letter. So the range is the set of y such that y is greater than or equal to 3. So we just have to keep that in mind. Now what I'd like to do is quickly sketch the graphs of f and f inverse so that you can see the third consideration that we took into account on the first slide here. So I'm going to rewrite, just for our reference, f of x, and then I'll just kind of do a quick and dirty set of axes here. And this f of x is the square root of x minus 3 plus 4, and so is shifted to the right 3 units and up 4 units, and is a square root function, and so it kind of gently curves to the right. There's my x-axis and the y-axis. And we can see the domain and range from the picture, if you like. Now for f inverse, which I'll do in a different color, f inverse is a parabola, and the parabola is moved to the right 4 units and up 3 units, but we're only going to draw half of it. The reason for that is I suppose I can appeal to a couple of different things. One, we had the domain and range business, right? The domain of f inverse starts at 4 and then goes on to infinity. Therefore, the graph has to start at 4 and continue on to the right. There is no graph to the left, because also, if there was graph to the left, we would have something that's not one-to-one, and now we have problems with the whole inverse situation. As they sit now, both f and f inverse are one-to-one functions, and they are inverses of each other. And so the final consideration that we had on that first page, first slide, is that they are reflections about the line y equals x. In other words, it's kind of like one is a stamp of the other if you folded a paper along that line. So using this switch and solve technique, what I'd like for you to do is find g inverse, the inverse of g, for g of x is equal to 5 minus x cubed. So first I'm going to switch x and y. So I'm going to say x is equal to 5 minus y cubed, and then I'm going to solve for y. Now to solve for y, we're first going to subtract 5 from both sides. So I get x minus 5 is equal to negative y cubed. And then, I don't know, multiply both sides by negative 1. I'm going to flip the whole thing around at this point. Y cubed is equal to 5 minus x. And so the cube root of y cubed is just y. And that's equal to the cube root of 5 minus x. This step is the one that I would normally not write. Reason being, I've isolated y. I know I'm looking for the inverse of g. I'd go, cut to the chase and write down that g inverse of x is equal to the cube root of 5 minus x. It's fine if you write it. It's fine if you don't. So there's the inverse. Now what we're going to do is we're going to confirm that what we've actually found is the inverse of g. And we're going to do so through composition. We're going to find g composed with g inverse of x and see that we pop out x, as we saw we could do a few minutes ago. I'm going to scroll back up. G is 5 minus x cubed. So g of g inverse of x should be 5 minus g inverse of x cubed. And since the inverse that we found is the cube root of 5 minus x, we have 5 minus the cube root of 5 minus x cubed. The cube undoes the cube root, so I have 5 minus, and since the radicand is a binomial, I'm using parentheses, the quantity of 5 minus x. And distributing the negative is going to give me 5 minus 5 plus x, which is simply x, which is exactly what we would expect by composing a function and its inverse. We could have alternatively composed g inverse with g of x and ended up with x as well. Reason for this, even though composition of functions is in general not commutative, that is, order matters, when we're dealing with a function and its inverse, it actually doesn't matter. And you are, in fact, encouraged by me to go ahead and perform this check. I'm going to go on to the next slide, where we are given a graph of a function h, and we are asked to draw the graph of h inverse. And the graph of y equals x is given for reference. I'm first going to identify some points that are on the graph of h. And I see that we have the point -3, -3, -2, 0, 0, 1, and 1, 4. H inverse is effectively going to reverse the x's and the y's. And so -3, -3 doesn't change. But -2, 0 becomes 0, -2. Likewise, 0, 1 becomes 1, 0. And 1, 4 becomes 4, 1. I'm going to plot these four. And now connecting these lines, or connecting these dots, gives me the graph of h inverse, which, as you can see, is a reflection about the line y equals x. For our last example, we have what typically is a test favorite of mine. Find f inverse for f of x equals 3x plus 2 over x plus 1. Give the domain and range of both f and f inverse. Let's count stuff. How many things are you being asked to find? F inverse, the domain and range of f, and the domain and range of f inverse. That's 5 things. To find f inverse, we're going to use that switch and solve technique. So f of x we're going to rewrite as x, because remember that represents y, is equal to 3y plus 2 divided by y plus 1. we need to use strategies that we have for solving equations generally. Keep in mind we're solving for y. The first thing I notice is that we have a fraction. So I want to clear the fraction by multiplying both sides by y plus 1. On the right-hand side, the y plus 1 divides out. On the left-hand side, I have x times the quantity of y plus 1. And then is equal to 3y plus 2 after that denominator divides out. Now remember what we're solving for. We are solving for y. Couple of things. One, I'd like to get rid of the parentheses, which means I'm going to distribute x. The second thing is I want to get the y's on the same side. So distributing x is going to look like xy plus x is equal to 3y plus 2. Now again, I want to get all of the occurrences of x on the same side of the equation, and everything that's not x, I want it together on the other side of the equation. And we'll see kind of why I want to do this in just a minute. So to get all the occurrences of y on the same side, I'm going to subtract 3y from both sides. That's going to give me xy minus 3y. And then likewise, I want to get all of the non-y's on the other side by together, which means I'm going to subtract x from both sides. So I'm going to end up with xy minus 3y is equal to 2 minus x. What that gained us was the possibility now, or the ability to factor out y on the left-hand side. And what I'm left with is the quantity of x minus 3. And on the right-hand side is equal to 2 minus x. Now I can divide both sides by x minus 3, thereby isolating y. So I have y is equal to 2 minus x divided by x minus 3. Now scrolling back up, we were given that this was f, and we were supposed to find f inverse. So I'm going to rewrite this as f inverse of x is equal to 2 minus x divided by x minus 3. That's one of the things that we were looking for. But we were also supposed to find the domain of f, the range of f, the domain of f inverse, and the range of f inverse. The domain of f is going to be obtained by looking at the original function. F was 3x plus 2 over x plus 1. And so for f, x cannot equal negative 1. That's going to give us our domain for f. The set of x such that x does not equal negative 1. Right now I'm going to use that to give me the range of f inverse. Remember, the inverse of a function switches domains and ranges. So the range of f inverse is going to be the set of y such that y does not equal negative 1. I swear that's what that says. For the range of f, it's difficult to get that directly from its expression. But what I can get is the domain of f inverse. Because f inverse is 2 minus x over x minus 3, I know that for f inverse, x cannot equal 3. That gives me the domain of f inverse, the set of x such that x does not equal 3. And that actually also gives me the range of f, the set of y such that y does not equal 3. So this is an example of a function whose range is more easily obtained after we find the inverse and use the domain of the inverse.